Hi, this is Linear Algebra, lesson 4.2. We're going to be talking about the null space and the column space. So if we talk about the null space, what does that mean? Well, if we have a equation, ax is equal to 0. All it is the null space is all the values of x which satisfy this. Okay, so what that means then is that set of all x that satisfy ax is equal to 0. And so we want to know what maps from one space to another such that we go to the 0 vector. And so in picture form, if I take and I say, for instance, that this right here is Rn, what I can do is I can map to Rm, which might be over here. And if I do that, I'm going to take certain points and say, so for instance, I have all these points. What they might do then is they might go ahead and map all to one singular point over here, which is the 0 vector. And so any point that comes from Rn over here and goes over to here to the 0 vector, that's what we're looking for. Now when we find all these values, we just call that the kernel. So that's something else that we'll deal with. All right? So that gives you a little bit of idea what the null space is. So now we have the definition of the null space right here. Why don't you go ahead and read that, but it just says it's a set of solutions of the homogeneous equation ax is equal to 0. And in set notation, this is the set of all x such that x is in Rn and ax is equal to 0, where x is a vector is what we're looking at here. So theorem 2 then says that the null space of a m by n matrix A is a subspace of Rn. So yes, those little points that we had that were shifting over to Rm, that set is a subspace of what we started off with. And then so proof, what we want to do is try to go ahead and prove this. So with the null of A, it's a subset of Rn because A has n columns. And remember our proofs from the last section, we had to do 3 things. Number 1, we had to show that it had a 0 vector. Number 2, we had to show that addition held true within the space that you're in. And 3, we had to see that the scalar multiple also stayed within and was closed within our space that we were in. So step 1, the 0. We're going to show that the 0 belongs in there, or is in there. So ax is equal to 0. Well, what does x have to be? Well, I shouldn't say what it has to be, but it is a solution to this homogeneous equation. So the 0 vector is part of our subspace that we do have. So if we have u and v within our space that we're looking at, what we have is 2 situations. AU is equal to 0 and AV is equal to 0. Those are the 2 setups that we have. So under addition, what we have is that if I take A of u plus v, what is that equal to? Well, we can say that that's equal to A of u plus A of v. Well, what's that equal to? Well, that's equal to 0 plus 0. Overall, 0. So what that means is that we are closed under this operation right here of taking the u plus v and then transform it over to another space, and we still go to 0 if this was true at the beginning for all those values for u and v. Then the third one, scalar multiple. If I take the A of cu, what does that equal? Well, that's going to equal, I can take the constant out. Well, we know that that's c times 0, and so that's going to be our 0 vector. So all this shows is that we are holding true to show that this is a subspace or of Rn in what we have. So let's do an example and see how this goes. Find a spanning set for the null space of the matrix. And so what we do is we have the matrix here, and so we know that we're dealing with AX is equal to 0. So we want to see which values of X map to the 0 under this matrix right here. Well, what we can do is we can reduce row, put this into reduced row echelon form, and notice also that this is a 3 by 5. I'm going to end up with a 3 by 6 because I'm doing an augmented matrix with the 0 row. So I'm just going to add that in now. So if I reduce this down, 0, -1, 3, and then I get my 0. And then 0, 0, 1, 2, -2, and my 0. And then this one had a wipeout. So we end up with this. So all I did was do this on my calculator to reduce this right here, but it was augmented, so I had the zeros in there. So this is what we ended up with. Well, what does this tell us? Well, let's write it out and figure out what each one of the variables are in terms of the free variables. So if I start with x1, x1 is going to be 2x2 plus x4 plus, oh, that should be minus 3x to the 5th. And all I did was I took this equation here and rewrote it. So now I can go ahead and solve for x3, which is right here. This is x4, this is x5. And so all I'm going to get is -2x4, and this would be plus 2x to the 5th. And my free variables would be x2, x4, and x5. What I can do then is I can take all of these and I can write them in somewhat of a vector form. So here's my setup. x1, x2, x3, x4, x5, and then there in terms of all my free variables that I do have. So x1 is in terms of x2 with a 2 there, and then at x4 they have a 1, and then at x5 we get a -3, and that all comes from right here. Similarly, I can do the same thing for x3, which would be a 0 and a -2 and a 2, which comes from right here. x2 is simply going to be x2. x4 is going to be x4, because those are free variables, and x5 is also free. So I end up with this. Now, what is this right here? Well, this turns out to be a linear combination. That linear combination of vectors, this we can call u, this we can call v, this we can call w. So what happens now with these three vectors, u, v, and w? Well, that is our spanning set for null A. Any linear combination of these goes and maps to the 0 vector, which is what we want for the null space. So we're going to end up with a span of the set U, and I'm going to use this notation, which are namely this vector, and this vector. So the span of that would be the span of the null space. Now notice, how many vectors do I have? Well, I have 3 vectors. Well, how many free variables did I have? Well, that's going to be the case. And that will end up spanning what we have. And so this is what this tells us right here. The number of vectors in the spanning set for null A is equal to the number of free variables in the equation AX is equal to 0. So that's how you find the spanning set for a null space. Okay, let's get into column space. So this is just another terminology that we've already used a lot of these things, but it's just different terminology. So we have the column space of a m by n matrix, written as the column of A, is the set of all linear combinations of the columns of A. So if A is a bunch of different columns that we do have here, then the spanning set for the column of A is just going to be all those vectors. Kind of makes sense. We're going to take a linear combination of all these. That's going to be part of the column of A. So theorem 3, the column space of m by n matrix is a subspace of Rm. M as in magnificent. Typical vector in column A can be written AX for some X because the notation AX stands for a linear combination of the columns of A. That is, the column of A is the set of all B such that B is equal to AX for some X in Rn. So we're going from Rn to Rm. And now this is not the homogeneous anymore. This is equal to a value. I should say a vector. So a couple of nice notes that we do have here. Notation AX for vectors in column A also shows that column A is the range. And so this is a word that we're defining is of the linear transformation X going over to AX. And then the column space of an M by N matrix A is all of Rm if and only if the equation AX equal to B has a solution for every B that we do have in Rm. So let's go to example 2 and see what we got here. First of all, example 2. I give you A, U, and V. So here's some questions. Determine if U is in null A. What does that mean? Well, that means that if I take A, U, what's that got to equal? Yeah, it's got to be the 0 vector. So all we do is go ahead and multiply that. So if I do this 2 times 3 and 4 times negative 2 and negative 2 times 1 and 1 times 0, add those together. Ah, we get 0. Okay. Maybe this works. And let me go to the next one. And that does not work. And so we don't end up with a 0 for this one here. So I end up with overall, if I do that last term, I get a 3. So this is not, no. I'm answering this question right here. Is U in the null of A? And the answer would be no, because this is not the 0 vector. Okay? And then could U be in the column of A? And the answer to that is simply no, because the dimensions do not match up. This one would have to have 3 rows in order for that to happen. And for V, we do have 3 rows, so let's see if V is in the column of A. And so if I go ahead and do this, I'm going to show that we're consistent for our augmented matrix. So I can go 2, 4, negative 2, 1, negative 2, negative 5, 7, 3, 3, 7, negative 8, 6. So there's one way to do this. Then I can go 3, negative 1, 3. There's my augmented matrix. Reduce that and see if you get values. So since V is consistent with what we have for the matrix associated with A, then we can say that we do have V is in the column matrix A. Now, could V be in the null of A? And the answer would be no, once again, because the dimensions do not match up, because I'm going A times V, and I can't do A times V in this case, because this is a 3 by 4, and this is a 3 by 1. So I can't multiply those two together. So let's end up with some definitions and also some contrasts of the column space and the null space. So first of all, definition. If we look at this one, we have a linear transformation. So if we have a linear transformation T from a vector space V into a vector space W, that's a rule that assigns to each vector X in V a unique vector T sub X in W, such that, well, if it's a vector space, both of these have to hold true. And then going over here, the kernel is just, it's the same thing as the null space. And so it's a set of all U in V such that T of U is equal to 0, the 0 vector in W. And then the range of T is the set of all vectors in W of the form T sub X for some X in V. So it's just whatever we're mapping to. It is kind of like the range of a regular function. Then the kernel of T is a subspace of V, which makes sense because everything could map to the 0 vector, I guess, but that would be a subspace of itself, but these are all just certain things, x's, that are in one space that map over to another space, which would give us a subspace. I don't think I did very good at explaining that, but oh well. And then the range of T is a subspace of W. And then for this last page, what we have is just contrasting the null of A and the column of A for m by n matrix. And I'll just do the first one, and then you can read through the rest. But notice that the null of A is a subspace of Rn. And then the column of A is a subspace of Rm. If I have a matrix here, which is a m by n matrix, well, what can I do? Well, I can multiply it by some vector x to see what maps over to my 0 vector in the wherever I'm mapping to. And so what does the dimensions of this have to be? Well, the dimensions of this has to be n by 1. And so then that's why we're a subspace of Rn. And we looked at the previous example of the column space. We just had to put in another column in here in order to do row reduction for the column of A. And so that means that the dimensions of that has to be m by 1. And so that talks about the spaces a little bit. I'll let you read through the rest of these. Try to study them, bring those to class if you have questions about them, and we'll talk about them. All right. Hope you enjoyed this. Thanks. Have a great day.